welcome everybody back to the workshop on interactive adaptive learning, to the afternoon sessions. I would like to start the session, the third session. And as before, we will start each of these 2 afternoon sessions with an invited talk. And for the first invited talk, I would like to welcome Robert Munro from Machine Learning Consulting on his talk on the rapid growth of human-in-the-loop machine learning. Robert, thanks for joining us, and we'll first play the video of your pre-recorded talk and then have you here for live discussion of questions on your talk. Thanks.
Hi everyone, I'm Robert Munro and welcome to my talk on the rapid growth of human-in-the-loop machine learning. So a little bit about my background. I've worked in machine learning for about 20 years now. I started my career as a software developer, working all around the world, originally from Australia. I worked in Europe for a little while. I worked in West Africa for the United Nations Refugee Agency. And then about 15 years ago, I came here to Silicon Valley to get a PhD at Stanford. I focused on natural language processing, adapted to healthcare and disaster response scenarios, looking at human-in-the-loop machine learning, as well as the NLP algorithms themselves. Following from that, I've worked at a number of startups. I launched AWS's first NLP and translation products. And I was CTO of the largest data labeling company here in Silicon Valley, Figure 8. And so along that way, I've learned a lot about the algorithm side of human-in-the-loop machine learning, as well as the data side as well. I currently run a machine learning consultancy, and I've just finished writing a book, Human-in-the-Loop Machine Learning. And hopefully that'll be useful for any of you tackling the intersection of AI and human processing. And as part of that book is a question that I've seen come up a lot, which I will address through this presentation and give you the answer at the end. So why has human-in-the-loop machine learning become so widespread? Just in the last 5 years, we've seen it really take off in terms of the different application areas and advantages that people see from building systems explicitly to try and combine human and machine intelligence. And one of the questions I see asked a lot is this on the back of advances in algorithms, or is this on the back of advances in data? So that's something that we will come back to at the end of this presentation. But first, before we talk about human-in-the-loop machine learning today, I think it's really interesting to go back and see where it started. And we can basically go back into any culture worldwide, and as far as there is recorded history that we can still access today, we can see people at least dreaming about ways that they can take technologies and turn it into intelligent, autonomous beings that they can interact with. So this example here from about 3,000 years ago is Hephades, excuse my pronunciation if I got that wrong in the original Greek, who was a metal worker, I guess you would say, in Greek mythology. And he built warriors and servants and an autonomous 3-legged table out of various metals. So more than 3,000 years ago, people were talking about intelligent beings that interacted with us or against us and in various ways. And if you're interested in this history of how different cultures independently were perceiving very similar ways that we might interact with robots or other intelligent beings, I recommend the book by Professor Adrian Mayer, Gods and Robots, Myths, Machines, and Ancient Dreams of Technology. It's really exciting to see how people have thought about automation over the years, and a lot of that really still applies today. As Mara says in her book, it's not that easy to draw a direct line from these ancient myths to the technologies that we have today. So I think we can jump forward to only about 100 years ago to see the origins of human-in-the-loop machine learning that we have today. And those origins are best expressed in a lot of art forms of that time. So in the 1920s, there were a very large number of plays and films addressing what intelligence looks like and what does interaction between human and machines look like on the back of, in their case, really the Industrial Revolution. So with so much of the workforce working now in factories or other kinds of automated and semi-automated environments, what does the relationship look like between humans and machines? How has the importance of humans risen collectively because they are a necessary part of a bigger economy now that they're part of much larger ecosystems of production lines? But at the same time, they ask the question of how much did this also commodify the work of individuals? And this is obviously a very important topic of conversation that still exists today in the notion of what's sometimes called ghost workers, the people who are being employed to create training data for machine learning, not always in conditions that are ethical. And so I think the questions which were being asked 100 years ago about exploitation of workers in mechanized environments, many of those still exist today. And in fact, the first example here, A Leader, which is a movie out of Russia from, I think, 1924, also has a very interesting allegory where one of the main protagonists is an engineer who wants to change the world, but does not get out of the lab enough. And his way of imagining what the world should look like and how it can be changed is too colored by the fact that he doesn't get out of the lab and interact with the world enough. And I think that's a lesson that a lot of software developers today might need to listen to as well. Certainly it's true across almost every software developer I've met that they genuinely want to make the world a better place. But that's hard to do if you haven't experienced as much of the world as you should, maybe because of your concentration as an engineer on the technology that you're building. So a much more famous film than A Leader from that silent era is, of course, Metropolis. In this case, a German film, but released under the same name when it had its English release in the United States and in England. And it is, I believe, still the most popular film from the 1920s. So the most popular film 100 years ago, not to give away too much, I hope, is about a robot that wreaks havoc on its environments. And of course, a famous play from that time, originally in the Czech language, is Rossum's Universal Robots, that coined the term robots, and it is a pun on a Czech word that roughly translates to slaves. And like in A Leader and a lot of other literature at the time, it definitely had a very strong undercurrent on making a comparison between people working in very automated industries and the robots themselves. So there are allegories then which spoke to a lot of the fears that I think we should still have today about the potential negative aspects of human and AI interaction. So it took a while for what we'd seen in the 1920s to become a reality. At the time, certainly there was automation, but there wasn't really the advances in circuitry or other related kinds of hardware where we could produce something that we might call a robot or something like machine learning today. And so we have to jump forward almost 60 years to the 1980s, to what I think is the most important inflection point for human-in-the-loop machine learning. And as with the 1920s, this started a lot with creative thinkers, with writers, with artists, with creators of comic books, and how they imagined the relationship between humans and technology at a point where we're just starting to see consumer electronics become popular. And as with the movies, this was imagined from very different parts of the world. So there were a lot of Japanese manga in the 1980s that started to think about what artificial intelligence might look like. An example here being a comic called Appleseed. In North America, literature and cinema was moving in this direction too, starting with the Canadian book Neuromancer by William Gibson. So this was the book that coined the term cyberspace, and was one of the first major novels to look at the relationship between distributed humans and smart technologies. And it followed shortly after, of course, the very influential movie Blade Runner. And hopefully I'm not giving a spoiler away where it is implied that certainly one character, maybe more, don't even realize that they are not humans, that they are something like robots. And all of these also look at the relationship between human exploitation and exploitation of machines, asking what does it mean to be human, what is really the difference. And in their particular cases, painting a little bit of a bleak future, all having aspects of a post-apocalyptic society. Again, a lot of that coming on the back of it being around predictions around what the world might look like after 1984 and then George Orwell's eponymous book, talking about how technology could be part of a method to control us. Fortunately, that hasn't happened, at least not in a post-apocalyptic scenario. But it was around that time that we did started to see people interacting with smart machines every day. And this looked much more colorful than the bleak literature and films of the time. And so a lot of this happened in computer games. In the 1980s, for the first time, people could afford consoles. Or consoles, I think, were only invented first at the very end of the 1970s with the Atari. And then, of course, more popular ones like the Commodore 64 and Nintendo machines really took off in the 1980s. And so in 1985 alone, a whole generation of children were playing new games like Super Mario Brothers, Where in the World is Carmen Sandiego, The Oregon Trail, and Paperboy. 4 games which are still famous almost 40 years later, and were all released the same year as each other. And I think the last of these is the most interesting. So obviously in Super Mario Brothers, you have this grand goal of rescuing a princess from a tower in this very strange world. Where in the world in Carmen Sandiego, you're a detective literally going around the world trying to find an elusive spy. And in the Oregon Trail, you're trying to make your way across the continent and survive. So 3 very grand missions, which certainly had the feel of interacting with intelligence, even though none of them use what we would call machine learning today. But the 4th of these is emulating a job which is not held in high esteem. It was my first job. Delivering a paper. So Paperboy was the, I guess, unfortunately gendered name of the game, where you're delivering newspapers, riding a bicycle and dodging obstacles. And the reason I think that's interesting is that it was popular without needing to have grand ambitions about being worldwide or the dangerous side of potentially just being part of the destruction of humanity. Here is something where you're interacting with the computer to do what would otherwise be a mundane task, and it's turned it into something exciting. Although I will give one caveat here. If you're building data annotation software to make your machine learning smarter, don't try to gamify it. That is one of the biggest mistakes I see people make. It is absolutely fun to try and dodge artificial obstacles in a computer game to try and improve your score. if you were trying to make a living annotating data and there are artificial obstacles preventing you from your work, it's a very different user experience. It gets very frustrating. So with that one caveat, I will say that culturally, the mid-'80s was a very important time for human-computer interaction. For the actual products that we shipped at that time, they weren't as colorful. They were very, very beige. So our first products that really could be called human-in-the-loop machine learning were released around this time. So famously, a Omnibot was released. I think the second edition of Omnibot was Omnibot 2000 in 1986. So this was this was early enough when you could put the word 2000 after something, and it just felt like a long time in the future because of the upcoming year 2000, and it seems kind of funny now. So it was a programmable robot, which people thought was going to be the start of a ubiquitous craze of people having robots in their house. And obviously it took more than 30 years before people started having things like Amazon Alexa or Google Home or Siri on their phone or smart vacuum cleaners in their house. Certainly wasn't the start of it, but it was the start of how we imagined it. I think more interesting at this time was when we saw the beginning of predictive text. So if you only speak English or a handful of closely related European languages that are typed with Latin script, you might not have seen predictive text until the last few years. Now I'm sure that your keyboard and your cell phone are predicting the next word and maybe entire sentences for you. And this is something you've really just seen over the last few years. Or maybe about 10 years ago, before smartphones, more like 15 years ago, you had feature phones where you could just type the numbers 1 to 9 and that would map to the various letters. And you'd get the predictive text from those letters. So this might feel like a more recent technology to you, but this actually dates from the 1980s. So it was incredibly smart system developed in China called the Wubi keyboard. And it maps the Latin characters by shape onto the thousands and thousands of Chinese characters. And so the name literally translates to like 4 strokes. So 4 Latin characters are enough that they can then be mapped using predictive text into the appropriate Chinese character. And this was an incredible breakthrough. At that time, it wasn't even possible to fit the Chinese alphabet into the memory of a lot of computer systems. And it was thought that there might not have been a place for the Chinese language because of the constraints in keyboards and the constraints in hardware at the time. So this ended up being an incredibly smart way where people could type fast by the shapes alone on the keyboard and produce the Chinese characters. And this is 2 properties I really like about it, in addition to being such an early use of human-in-the-loop predictive text. And the first of those properties is that it worked in any language using Chinese characters. So there are a large number, maybe like a dozen or so really widely spoken languages, which are completely different to each other in how they sound. They're, for the most part, not mutually intelligible, but they all map to the same Chinese characters because it's not a phonetic system. And so this allowed a really large number of languages to be digitized. It wasn't just one. And there are later methods which do use phonetic mapping and therefore are specific to the individual language. But I love that this first method for predictive text was much more language independent. And the second part I love about it is that it is still one of the fastest ways to type today. So using the Wubi method invented in the 1980s allows the fastest typers to type in Chinese faster than the English typers type on the same keyboard optimized for the English language today. So it's an incredible advance, which is still around today, although it's probably no longer the most popular predictive method for typing Chinese characters. And then a final product example from that time is spell checkers for typewriters. So even slightly before personal computers and word processing became popular, electronic typewriters started to have technologies where you could basically plug this piece of hardware in between your keyboard and the electronic typing component. It would look at the characters which are going through, it would try to work out if you've misspelled something, and it would choose not to type that character or make a pinging noise to tell you that you might have mistyped something that you need to double check. And so this was a kind of smart human-computer interaction. They were programmable with new vocabularies that existed even before personal computers. And to hear more about that, I recommend looking at Ron Kaplan's computational linguistics lifetime achievement speech from last year. So Ron Kaplan, recently retired computational linguist, was part of the company that built some of these first smart human-in-the-loop technologies just before the birth of personal computers. And I was super fortunate to have Ron Kaplan as a professor in graduate school at Stanford, and also a colleague, both at startups and at large companies like when I was at Amazon as well. And so, so although we have seen the explosion of human-in-the-loop machine learning recently, I think it's really interesting to see where its origins came from. So jump into today in 2020. I'm going to go through a bunch of examples of how human-in-the-loop machine learning is used today. And what's really interesting is the range of motivations that people have for looking to applications that combine human and machine intelligence. So these include avoiding bias, creating employment, augmenting rare data, maintaining high precision or human level precision of data, and incorporating subject matter expertise, ensuring accuracy and transparency, making work easier, improving work efficiency, providing transparency and accountability, and increasing safety. So these are 10 different motivations that people are having for using human-in-the-loop technologies. And as you look through all of these, it might be interesting to think about, especially if you come from an academic background, how abstract these are. I think a lot of the time, scientists, in particular machine learning scientists, really look at the human-in-the-loop component as data labeling, as a way to get more data to make a model more accurate. And while that's certainly true, that wouldn't be the first thing that I think a lot of these application developers would say are their motivation for trying to provide the best experience for the people using their applications. So the first, avoiding bias, or probably more accurate, would be minimizing the bias, because it's obviously hard to remove bias, and even if you're below a level of statistical significance, there might still be bias there that you're just not measuring for. So reducing bias. So this article from the World Economic Forum this year was talking about AI governance, and in particular how it's essential to have human in the loop of AI decision making, so that biases which might exist in models can be detected early on. So whether that bias is in your data collection, whether it's in your annotation, whether it's in your algorithm itself, or some combination of how you've built and productized these, having humans can validate your model, ensure that you're not getting biases in that model that are detectable, that humans can remove that would otherwise be created by machines. Second example is maintaining high precision, or another good way to say this might be maintaining human level precision. So this is a really interesting example here for autonomous vehicles. And in this case, they're talking about autonomous helicopters. And obviously for any kind of aircraft, there is not much of a margin for error. And so one of the things that these autonomous vehicles, no matter what the use case is, one of the things that they have to decide on is, when do the machines not know that they're doing well? When are they uncertain? When do they think they will be less accurate than a human? and in those cases, turn it over to, in this case, the human pilot and to control in a certain environment. And so I think this has really interesting implications in that we expect our machines to be more accurate than us if we're allowing them to be autonomous, especially in situations like autonomous vehicles. But this isn't amortized accuracy. It's not more accurate overall. We want them to never drop below human level accuracy. So there are not situations where we're prepared for our machines to be less accurate than humans if they're safer overall. And so this leads to really interesting interface implications. So if a model can identify when it is going to be less accurate than a human, then how does it communicate that to the human to have them take back over the controls in autonomous vehicles? So I think this is a really interesting example that's certainly not going to go away. Thinking about the ways in these critical situations that the machines, which are mostly automated, should back off to humans most appropriately. Third example here is incorporating subject matter experts. So this example is from NASDAQ talking about trade surveillance. We've seen this a lot recently on the back of COVID. A lot of people knowing that announcements were coming, deliberately selling shares based on insider information, which is illegal here in the USA, as it should be. And one of the things that NASDAQ does is look for patterns in share trading, which indicate the evidence of insider trading or other fraudulent behavior. However, it takes a lot of expertise from someone in this industry, to know what is illegal, what isn't illegal, what are some of the signals that look bad but might be okay, or vice versa. And so this is something where the algorithms can really benefit from being trained by those small number of human subject matter experts. And so certainly if you look at this industry, historically, it's actually been a lot of unsupervised machine learning, looking for things like anomaly detection, outliers, as basically alerts, which human experts then investigate to see if there really is some kind of suspicious behavior. And this particular article is interested in talking about some of the newer ways that supervised learning means that human feedback of what was actually suspicious or what wasn't can feed back in to make these alerted systems more accurate. Next example is in health, and in this case, improving efficiency. So like this article says, there are certainly some people out there who very strongly believe that we will replace a lot of healthcare professionals with AI. But at least currently, the way that most of this industry is moving is to make those healthcare providers a lot more efficient with AI. So it's not like you're only going to have AI interpreting an X-ray. You might have AI interpreting an X-ray, but using that to help inform a physician about which areas of the X-ray they should investigate, or what look to be the anomalies, or what are possible diagnoses, but leaving the actual decision making to the physician themselves. And on the back of this, we see a lot of interesting implications for human-computer interaction as well, in particular explainable models. So I've seen a lot of very interesting applications in healthcare where there's dual models, where there is a less accurate but very interpretable model that healthcare professionals are using to interpret some of their results, and more accurate, purely automated models that aren't very interpretable, which they can use for non-critical investigations. And it certainly wouldn't surprise me if we see a lot more development of these kind of hybrid systems. We have multiple models in parallel with that trade-off between explainability and accuracy, so that the right choice is possible for the particular scenario and the particular legislation. So transparency and accountability is very much related to this idea of how interpretable is your machine learning model in healthcare. In this particular example, it's immigration officials, in this case, Canadian immigration officials. And I think what's interesting here is the decision about where to back off to a human can be made based on interpretability of what will be the most adverse outcome. So actually, I don't know for sure what they're doing in Canadian immigration with human in the loop, but what I would hope would be that they are automating some of the visa applications. But any time that a visa application is rejected, which is the most negative outcome for a human, then that is further verified by the immigration official. So it might mean that through automation, some people get through that wouldn't, but it's not for the individuals applying to go to Canada. It's not adverse to them where they're programmatically stopped from visiting that country. Like I said, I hope that's the way that they're doing it. That's the most humane way of doing it. And certainly this speaks to a broader set of implications for machine learning models as well. You can decide, well, what are the most negative potential outcomes, maybe based straight off the kind of labels like they might have in this situation, and then back off to humans, not necessarily where to increase your model accuracy, but where there is the least impact on people's lives downstream. Next example is creating employment. So we covered this a little bit in the talk already. By some measures, the majority of people who work in machine learning work in creating training data. And this is also the most multinational and most diverse workforce in all of AI. And so I think it's a real shame that this is an incredibly overlooked part of the AI community, that we have this this lie that many people are telling themselves that most of our systems are fully automated when they're not. The human component of validating the data or creating training data from raw data is absolutely vital to the majority of deployed machine learning systems in the world. And so the humans that are powering that are an absolutely incredible part of, incredibly important part of that process. And what I like about this is exactly the diversity of the workforce. There are a lot of people worldwide now who are basically outsourced workforces who specialize just in creating training data. And done right, they're guaranteed fair employment, advancement in their work, depending on the country, benefits, if it's a country where employer-provided benefits are expected. And in a lot of cases, these are people who otherwise wouldn't be able to take advantage of the information economy. So done right, outsourcing work provides gainful employment, dignified employment to the most important people for a lot of AI applications, and it can do it in what's much more of a meritocracy, where they can be judged quantitatively on the quality of the work that they're creating, much less so on some of the other factors about their gender or their age or ethnicity that otherwise might lead to some of the biases that we see on the computer science and software development side of our industry. Okay, next example, and I think it's a related one to great employment, is augmenting rare data. So in this particular example here, they're talking about why Facebook wants to do things like looking for fake news equally accurate across many languages. And obviously, if it's a very rare language, there might not even be enough raw data with examples of fake news that you could annotate that data and get an accurate model. And so if you want to provide an equally good service across different languages, then this is one way that you can do that. It's backing off to humans who speak that language in order to get to that level of accuracy that you can in an automated fashion when you have more data available. And related to creating employment, I like that this means that you're employing more people who speak less widely spoken languages. So you're creating more employment against people who have probably been more overlooked historically in technology, and doing it in a way to make services like social media better for other speakers of their languages. Next example, ensuring consistency and accuracy. So this is a really interesting example that has been around for maybe 20 years now in use cases like e-discovery. I think some of the early advances in human-computer interaction were really in these auditing firms, and maybe in use cases that weren't considered that interesting for computer scientists and therefore overlooked. But providing human-in-the-loop interfaces so that, for example, if you are doing an audit, say you're doing fraud detection, you can have AI surface the examples that most look like they might be evidence of fraud or collusion or some other illegal activity, and then have the professional auditor validate those, and then have that go back into the system again. But obviously, you don't want any algorithmic bias or an encoded bias in the data to be magnified or perpetuated. That would mean you're only discovering illegal activities among some set of people and letting some others get away. And so having humans in the loop is one way to push this towards more consistent results, regardless of the kind of data that you're looking at. And related to helping auditors is that making work easier. So by automating more of the work, taking away a lot of the work that can be automated, it might be seen more mundane. It allows subject matter experts to focus on the tough data points that most require human attention. So in this particular example, it's looking at cybersecurity, and like with a lot of the examples we've seen, is really not possible to get the kind of accuracy that you would like in a fully automated system. But that doesn't mean there's no use for machine learning. Quite the opposite. Like a lot of people dealing with data and network traffic, the amount of data and information that security experts need to look at is really rapidly increasing every year, not at the same rate as most of their budgets, unfortunately, which means that tools to automate more of this become a necessary part of how they're scaling their industry. And the final of our 10 motivations is increasing safety. So this was I thought really interesting example of how Formula One are using professional gamers, esports drivers, to trial rule changes. So trialing new changes in the way that Formula One cars are allowed to be built and the kind of rules that they need to follow when driving around the track. They can have these gamers drive virtual systems with these new proposed rules and see if it really does result in fewer crashes and other dangerous situations. So yeah, this isn't the kind of human-in-the-loop technology where we thought we had an autonomous robot like R2-D2 in the back of our vehicle as we're flying around. But it is a form of human-computer interaction with AI, which is increasing the safety. In this case, of Formula One drivers, but I also know of autonomous vehicle companies for delivery cars and passenger cars doing this kind of simulated driving for cars that you would go past on the road as well. So that's obviously like a big range of different examples of how human-in-the-loop technologies are being used today in machine learning. And so to give you an idea of how popular this is, all those articles that I just showed were all published within 3 weeks of each other. So I didn't have to go over a really long period of time or look to obscure publications to find such diverse examples for the ways that human-in-the-loop are being implemented for different motivations and in very different use cases. I didn't think we we've seen that many advances in machine learning where one technology or approach is so widely used so quickly. But that's certainly been the case in the last few years as machine learning has matured, that whether it's deep learning or decision trees or unsupervised learning, or even just regression models, regardless of the kind of models which are being deployed and used, this huge explosion in the last few years has been accompanied by the realization that for any number of motivations, you need humans in the loop in order to make the models more accurate, to make them fairer, to make more accountable, etc. And so I think it's incredible to see how much we're learning across all these use cases as they are being built into so many different kinds of applications for the very first time. So to end with, I'll take it back to the question that I started the presentation with. So why has human-in-the-loop machine learning become so widespread? Is it advances in algorithms or is it advances in data? And I think the answer is neither. I think the advances in algorithms and data are really, really important, but I don't think those have been the driving forces for what has actually made it widespread. I think it's advances in hardware and changes in our expectations for human-computer interaction. And we've certainly seen that there's advances in hardware for a while. So, you know, like I mentioned right at the start of the talk, we were thinking and have been thinking about human-AI interaction for all of recorded history. And 100 years ago, the biggest films and plays of the day were on this topic. But it really wasn't until the 1980s, on the back of consumer electronic advances, or on hardware advances, that we saw the first attempts at this kind of technology. And I think that it was that timing that led to where we are today. So the people who first used Wooby or spell checkers in the 80s, who first had consoles in their home where they felt like they're interacting with really smart technologies in the games that they were playing. These are the people who are now running technology companies today. And at the same time that people who are the first generation who have interacted with smart computers for their entire lives, at the same time that they're running companies, we now have hardware advances where it's not just computers that we can have in our homes and are affordable. It's computers powerful enough to run machine learning algorithms, you know, in our phones or incredibly cheaply in the cloud, where the cost of computing itself is not considered prohibitive for certain applications. Yeah, as someone who has just written a book about the interaction between algorithms and data, those are certainly the things that we need to think about as we're trying to get the most out of our individual applications. But I think the broader movement and recent popularity of human-in-the-loop machine learning has come more on the back of some really incredible advances in hardware and some interrelated and important changes in the way that we think about interacting with technology. So thanks for attending my talk. I'm happy to take your questions after this. Like I mentioned at the start, I've just finished writing this book on human-in-the-loop machine learning. You won't find any interesting historical examples of robots in there, or not many. It's very much about the set of algorithms you would use for things like active learning and evaluating quality control in creating training data. And there's also open source PyTorch library associated with that. So thank you very much.
So thanks, Robert, for your very inspiring talk. We have one question, I think. Yeah. Okay,
right,
that's
happy to take any questions.
So I have Okay, Corey has a question, so let's start with Corey's question.
Oh, wonderful. Corey, I'm looking forward to your talk as well.
So, Daniel, can you give Corey audio? Yes.
Hi, can you hear me?
Yes.
Hi, great talk. Thank you very much. I was just curious on your takeaway slide at the end. You talked about the growth of human in the loop machine learning. Is it also possible that it's become widespread just because of the broad range of domains that we want to use machine learning, and we believe that it can be advantageous, but some of these are incredibly complex. So the machine learning models themselves may not be adequate, or all of the societal factors that necessitate the humans in the loop?
Yeah, I mean, I think that's a really good question, and thanks for joining what I guess is 6 a.m. on your time as well, if you're joining from Seattle. I appreciate that you got up early for my talk. Yeah, I think this is actually like one of the most common things I see day to day, is that when people are looking to build machine learning for a use case for the first time, there simply isn't annotated data available. And it's not clear from the start what level of accuracy you'll even reach once you go deep into what kind of labels, information that you want to annotate and try to shape models to do accurately and with low latency. So I think that motivates a lot of, especially startups, to implement human in the loop models where you can at least get some level of accuracy with purely manual processing, and then you can start building data on that. And that's meant a lot of companies have ended up with really interesting use cases where they never get to full automation just because of the limits and what can be automated. And so they have these really, really efficient human in the loop processing systems by necessity. A lot of companies doing things like OCR, like receipt transcription, are in that space. And I wish they'd gotten more attention. So one company in particular is it's called Captricity, where it was able to process medical forms and distribute the work where it couldn't be automated in such a way that they got HIPAA compliance, because the name would go to one place and the prescription would go to another place. They were able to demonstrate that this met some of the concerns around privacy as well. So I think there's a ton of really overlooked innovation that's come out of necessity. So thanks for that question.
Great, thanks. And I cheated. I'm on the east coast of Canada, so I'm not actually in Seattle.
Oh, okay. I knew you were at Microsoft, and I just assumed Seattle. All right, so it's
visiting family on the east coast. So.
Oh, nice. Oh, it's a good time not to be on the west coast.
So, Robert, I would like also to ask a question. So you mentioned in your talk that the changes in the expectations are a driver in bringing machine learning forward to many applications. And I think these expectations is also a very important point, because what I observed in some applications is that I think there is a difference in the expectations that we have on machine learning systems when they are the decision maker, than as we compare it to a human decision maker. So, for example, when we talk about fairness and avoiding biases, then my impression is that sometimes the use of a machine learning system is rather unveiling that there has been a bias in the human decision making before, and then when we use that on as a training data and we come up with a machine learning model, then it kind of shows that there has been this bias, and then starts the discussion about how to do it right and what and to avoid. So to give a very brief example, we had in Austria, we had a discussion about a system for classifying unemployed people based on their chance to re-enter the workforce and to get re-employed, and also which benefits they should get. And then this was based on data that was done by officers from the employment agency. And it turned out that actually there was quite a bias based on gender and age in that data. And that was actually revealed by having a machine learning system using that data to make the decisions. So I would be interested in your opinion on your thoughts on that, that actually when we start using machine learning systems, isn't that very often the case that it actually unveils some biases that are already there, but we might not have been so aware of them?
Yeah, I mean, this is one of the positive outcomes when you do a machine learning model that it is biased. Like, yeah, maybe it can lead you to look at the systemic problems that led to that. And yeah, I mean, I think we should be holding our machine learning algorithms to a higher level than any of us independently. And there's obviously like additional problems in that algorithms might not just reflect the bias in the data; they can amplify them. So yeah, with that caveat as well. I think it's useful to think about any data set as probably biased before you start annotating it. So like I say in my book, we often think about active learning as a way to reduce the number of labels or to ship a model faster. But another reason not to just randomly sample the data you have to annotate is that whatever process you use to collect it had some kind of bias. It was keyword filtering or time of day or something more along protected classes of demographics. And so being mindful about your sampling strategy should be one way to reduce as much of that bias as possible, or certainly to detect it, to know what's there and know your model will be strong and weak. Yeah, so I mean, I think this is an incredibly interesting area of human in the loop machine learning right now, and one where we're just starting to really kind of understand what the causes or joint causes are of data and algorithm derived biases.
Thanks. So let's look for the other questions. I think for the moment there is no further question. So then let's probably thanks Robert again for joining us that early and being with us for this session. Then I would go to the next talk. So the next talk is given by Vincent Lemaire from our Orange Labs France. Yeah, Vincent, the stage is yours.
Hello, everyone. This is a presentation in the workshop Interactive Adaptive Learning, co-located with the Open Conference on Machine Learning. This is a presentation of the paper Learning Active Learning at the Crossroad, Evaluation and Discussion. This is a joint work between Louis Deromeau and Vincent Lemaire from SAP Labs and Orange Labs. I'm Vincent Lemaire, and I'm in Brittany. First of all, I think it's interesting to place active learning within the weekly supervised learning framework. In the supervised classification problem, the objective is to learn a classifier from a set of labeled training examples in order to predict the class of new examples. In practice, conventional classification techniques may fail because of the imperfection of real-world dataset. Accordingly, the fields of weekly supervised learning has recently seen numerous papers aim at addressing different types of supervision deficiency, namely poor quality, adaptability, or insufficient quantity. For example, concerning the quality, we may have inaccurate labels because of label noise. Concerning adaptability, Sometimes we have three labels, but they are not as the right proxy. So we should use transfer learning or multi-instance learning. And for insufficient quantity, label could be at the proxy, but we may have very few labels. Insufficient quantity of labels appear when many training examples are available, but only a small portion is labeled. For example, due to the cost of labeling. Usually, this issue is addressed by semi-supervised learning or active learning, or sometimes self-training and co-training. This is the place of active learning in the weekly supervised learning framework. Active learning principle. There are four key elements which are required: an initial labeling training set, a classifier, a selection strategy and a pool of candidates, and the expert. So active component is to ask query to an hierarch to improve the performances of a classifier, but also by minimizing the cost of obtaining labeled data. So active learning optimizes a performance which is induced by a classifier through selecting the most beneficial unlabeled instances to be labeled by an oracle to build the training basis. For the selective data acquisition task, there are two main cases: active sampling or selective sampling. In the former, the model could ask the label of a sample to be created. In the latter, it could just ask the label of an existing sample in a bag, for example. And the paper concerns the second one, selective sampling. The question that I would like to address in this paper is which methods to use or to recommend in an industrial context where, for example, the end user has no expertise on active learning. In the first active learning algorithms, the idea was to keep the usual supervised learning methods and to add strategy relying on various heuristics to guide the selection of the most informative example. From the first initiative up to now, a lot of strategies motivated by human intuitions have been suggested in the literature, as for example, uncertainty, error reduction, density-based, etc. The utility measures defined by the active learning strategies in the literature differs in their positioning according to a dilemma between the exploitation of the current classifier and the exploration of the training data. A careful reading of the experimental results published in the literature shows there is no best active learning strategy that consistently outperforms all others in all applications, and some strategy cater to specific classifier or to specific application. Based on this observation, several comparison benchmarks carried out on numerous datasets have highlighted that the strategy which, on average, are the most suitable for several classification models. For example, we have the paper of Pereira, Santos, and al. In 2019, which shows that the association of random forest and margin is very good and is very often one of the best associations. In recent years, meta-learning algorithms have begun in popularity. Some of them have been suggested to tackle the problem of learning active learning strategy instead of relying on manually designed strategy. Motivated by the success of methods that combine predictors, the first active learning algorithms within this paradigm were designed to combine traditional active learning strategy with boundary algorithm. This is the case, for example, of the paper of Su and al. In 2015, Active Learning by Learning. This is a meta-active learning algorithm designed to solve the problem. This algorithm considers multiple existing active learning algorithms and adaptively learns a query strategy based on the performances of the algorithms. Each active learning strategy is like a body arm. Within the meta-learning algorithm framework, some other algorithms have been developed to learn from scratch an active learning strategy on multiple source datasets and transfer it to new target datasets. Most of them are based on modern reinforcement learning methods. The key challenge consists in learning an active learning strategy that is general enough to automatically control the exploration trade-off when used on new unlabeled dataset. For example, there is a very recent paper of Koyunchkova and al. Discovering general purpose active learning, that they use a deep Q network to learn an active learning strategy with the usual paradigm, state, action, and reward. We are not going to detail this paper in this talk, but the paper contains many details to understand their idea. So, where we are? What are the claims of each view? For example, Pereira Santos said one of the best associations is random forest plus margin. But Zhu and al. In 2015 say it's better not to choose a single one strategy, but to use a boundary algorithm that do the choice. And Koyunchkova and al. say, no, it's better to learn a strategy from scratch. So Koyunchkova said that the result is better than B, and Zhu and al. said that the result is better than the best strategy from A. So what did we compare in the paper? We compare something which is very trivial, random forest plus the random strategy, also logistic regression plus random strategy, random forest or logistic regression plus margin, and the recent paper of Koyunchkova and al. This is a deep QL using random forest or logistic regression, and their method will be named LAL later in this presentation. Learning active learning. What is the protocol of our benchmark? We use only binary classification problem. We used 8 datasets to train the policy, which are described in the table below in this slide. 20 datasets to evaluate our results. 2 models, logistic regressions or random forest. And we use the learning curve using the RL under the learning curve using the accuracy to evaluate our results. We use 20 datasets for the evaluation. The datasets were selected so as to have a high diversity according to the following aspects: number of examples, number of numerical variables, number of categorical variables, and class imbalance. This table presents the result, the area under the learning curve using the accuracy. The left-hand part in orange are the results with the logistic regression, and the right-hand part in gray with the random forest. For both, we have the results with the random strategy, the margin strategy, and the LAL method. First of all, it should be noted that the choice of the model is very important. The result of the random forest in green are all better than those of logistic regression in yellow, in orange. The random forest learns very well from few data, as highlighted in the paper of Stapavik and al. And you also notice that even with the random sampling strategy, random forest is almost always better than logistic regression, whatever the used strategy. In addition, using margin sampling with this model, random forest. This margin strategy allows a significant performance improvement. This association is very competitive. How about LAL now? How about the method of deep query? The results of the learn strategy clearly shows that the strategy, an active learning strategy, has been learned because the results are better than using the random strategy. But the learn strategy is not better than the association of random forest and margin, and not always better than random. To investigate the learning speed also we saw that it's often hard to beat the majority vote in case of very imbalanced problem. To investigate the learning speed, we show results for different size of the training set in the paper in table 6. They lead to similar conclusion, and the reader may find all our experimental results on GitHub. So time for the conclusion. The experiments carried out confirm the relevance of the LAL method. It is possible to learn a strategy, but contrary to the results of the paper, they are not always better than the random strategy, the random sampling strategy, and not always better than the association of random forest and margin. LAL is sensitive to the performance criteria used and needs hard work to optimize the many hyperparameters of the methods. The evaluation in this paper confirms the results of Pereira, Santos, and al., namely that margin sampling associated with random forest is a very competitive strategy, and thus, from an industrial point of view, regarding the computational complexity, the performances obtained, and the absence of domain knowledge required to be used by the end user, the margin RF associations, remain a very strong basis difficult to beat. We address also some open question of resource ID at the end of our paper, and we'll be happy if you have questions or ideas to share. Thank you.
Thank you for the presentation. So, questions?
Yeah, nothing. I don't know if there is a question or not. Guillaume?
Oui. Yes. So, yeah, I do.
Maybe the presentation has been very clear.
Yes. I think one important point that you highlight there is that you have a difference. Well, you quite have a strong difference probably between the classifiers that are used, and that this has to be well separated from the active learning strategy. I mean, you in your results, you looked in particular at the random forest and the logistic regression. But is that, let's say, I think that will generalize over other classifiers as well. For example, Bayesian classifier would be probably work with few labels quite well, but might with many labels have difficulty, well, work less well, for example, than I would assume random forest. But so have you plans to look at other classifiers as well for that?
Well, I just tried these two classifier because that was the classifier has been tested by the paper of DQL to learn a strategy. So that's the first answer. And also because in the Santos paper, the association on random forest and margin was very interesting to test. And the idea, the main idea of the paper is to say, okay, if I have no expertise and I am an end user, it's easy to use or not. The DeepQL algorithm have many parameters to test and to set. It's difficult to use if you are not an expert on active learning. And random forest and margin association is very interesting, even with the random learning strategy. So it's very interesting for me in this case. And I think there is a link with the talk of IJCNN, because an interesting idea could be to use the random forest as a gradal set classifier and to see if, in this case, the epistemic strategy could be interesting using the random forest also. I think that the random forest, I'm not able to show you today, but by default, perform exploration and exploitation by nature. But yes, you can speak if you'd like to say.
Can you?
Yeah, my question, you mean? Okay,
Yes.
I posted the question in the Q&A chat, but I can just briefly recall. So my question, Vincent, thank you very much for the nice presentation. So what you presented is very closely connected actually to what is also called algorithm selection and configuration. So there is a whole sub-community working on that topic, and it's also very closely connected to hyperparameter optimization, which is nowadays a hot topic, and automated machine learning and these things. So my question is, are you aware of, let's say, systematic work along that direction specifically for active learning? It's indeed true, when you started talking, I was wondering a little bit and asked myself why so far I didn't really came across such kind of work, because it's a very natural thing to do in a sense when you work on algorithm selection configuration, to say, okay, I apply these strategies also to the selection of active learning. So yeah, my question is there systematic work on that, or the work you presented here and you compared with, is this more a kind of isolated piece of work on that topic?
No, I am a team who are very interested by automatic learning, and we would like to have no user parameter. So that's why we conduct many studies to see if we may find in the literature, or if we may design solution without parameters. And for active learning, the new paper about DeepQL was very interesting. And here again, the idea was to compare with this association which has no parameters. But I don't know if I answered the question.
Yeah. So yes, I basically got the idea. Yeah, I was just wondering whether there is more work on that topic, because, as I said, I mean, there is quite a large number of, let's say, meta learning techniques tackling or trying to automate or partly automate various kinds of machine learning problems, and active learning could be one of these problems. So I could imagine that many of the things that have been developed in the realm of algorithm selection and configuration could be applied potentially to active learning?
For active learning, I don't know. For supervised learning, the answer is yes.
Oh, yes, this is for sure.
But but when the number of labels is very low, often you need a big knowledge on your domain. So I'm not sure that's possible if you have no absorption on your domain.
Yeah, this is perhaps true.
Yeah.
Okay.
But
anyway,
I think I think also that could be interesting for you is the result of this paper, because if you consider your paper about the two uncertainty part, it could be interesting to see if you take a Credal set classifier, and this Credal set is a random forest. That could be very interesting for you because this classifier has no parameter and could be incorporated in your paper as a Credal set classifier.
Yeah, this is perfectly true. And just as a side remark, we recently, very recently, published a paper together with a student of mine in which we exactly are using random forests to quantify uncertainty and to make this distinction that I was talking about between aleatoric and epistemic uncertainty. And this work, or part of this work, will also be presented on Friday in our workshop. Yeah, you are perfectly right. So random forests are very interesting from that point of view.
Yeah. And if you are able also to design a random forest in the sense of your probability of the data knowing the models, that is a parametric one, so you can also incorporate the other part of your paper, I think so.
Yeah. Okay, thank you very much.
Okay, thanks Vincent, thanks Eike. So given the time, I think we have to move to the next speaker. So thanks Vincent again, and I would ask Daniel to play the video of Agnes Stegen from Malmö University in Sweden on the effects of reluctant and failable users in interactive online machine learning.
Hi, my name is Agnes Stegen, and today I'm going to present this paper titled The Interactive learning is when a human or a user provides labels for data to be used for training by a machine learning algorithm. This includes both active learning, when the learning system initiates which data instances to label, and machine teaching, when the user themselves are more proactive. So generally in interactive learning, the assumptions of the user are that they will always provide a label when queried by an active learning strategy or in accordance with a machine teaching strategy. Furthermore, it is typically assumed that the label provided by the user always is correct. In some settings, this can be reasonable assumptions, but in many scenarios, they do not hold. So in this work, we explore how the reliability of a user providing labels affects the performance of online machine learning. Online learning means that we have streaming data that is presented to the machine learning algorithm in a single pass manner. We'll look at the aspects of reluctance and fallibility, where reluctance is how probable it is that a user will not provide a label in accordance with a given interactive learning strategy, and fallibility is how probable it is that the label provided by a user is incorrect. We perform experiments on two datasets where we vary the degree of reluctance and fallibility of the user. The aim is to study how this influences the performance of different machine learning methods and different interactive learning strategies. So from our experiments, we found that the robustness towards reliability differed among the different interactive learning strategies, and especially machine learning methods. In the experiments with the fallible user, the naive Bayes classifier was significantly more robust compared to the support vector machine and k-nearest neighbor. For a support vector machine and k-nearest neighbor, it is preferable to have a user that might provide less labels, but when they do, they are correct. So in our problem setting, we have an IoT environment where our aim is to detect the current ongoing activity or the status of this environment. And we do this by using sensors that are present in the environment and that stream data, which is picked up by the machine learning algorithm. The machine learning algorithm then in real time produces an estimation of this status or activity that we're looking to estimate. So the machine learning algorithm then, of course, has to be able to handle that data comes in this streaming single pass fashion. We also have a cold start problem, and this means that we don't have any labeled data to train our machine learning algorithm with before we put it into use. So the machine learning algorithm starts from scratch, you could say, when the time starts, and has to then instead gradually over time be incrementally trained as more and more data becomes available. So to do this, we also need labeled data. And here is where the user comes in. So we have a user present that has the possibility to observe what is going on in the environment, what is the current status or activity, and also has the possibility to provide labels to the machine learning algorithm. So this is what's called interactive learning. And interactive learning including active learning and machine teaching can be used to lower the amount of labeled data needed while still retaining a high performance. So often in interactive learning, we see these assumptions that we have that the user is a so-called perfect oracle that never makes any mistakes and always acts as you expect them to. And in some cases, this might be a more realistic or okay assumption, but in many scenarios, it is not that realistic. So in this work, we wanted to study this further, and we vary the reliability of the user to study the effect on performance using different machine learning methods and different interactive learning strategies. So moving into the experiment part. So we're going to start with the experimental setup. So as mentioned, we have this cold start problem that we're looking at. So also in the experiments, we didn't pre-train our machine learning algorithms with any data. They started completely from scratch and had to gradually train over time. And we did the evaluation in a test and train fashion. And this means that when a new data instance comes in, the first thing that happens is that the machine learning algorithm takes this data instance and tries to estimate what is the appropriate label for this data instance. And then, depending on the interactive learning strategy, we might get a label. And if we do get a label for this data instance, then we incrementally train the machine learning algorithm with this labeled data. We looked at 3 different types of machine learning methods. These were naive Bayes classifier, support vector machine, and k-nearest neighbor. And these were chosen because they were suitable for our problem setting. We have the streaming data, which means the online learning that we need the machine learning algorithm to be able to handle. We also have the cold start problem, which means that we need a machine learning algorithm that can be up and running fast, even though it doesn't have that much labeled data to be trained on yet. We looked at 2 different types of interactive learning strategies. So the first one here is the active learning triggered by uncertainty. So in this case, we have that the machine learning algorithm is producing an estimation, as always, but is also producing an uncertainty measurement. And this uncertainty measurement is sent to an active learning strategy. And the active learning strategy takes this uncertainty measurement to decide how certain is the machine learning algorithm with regards to its own estimation. If it's considered uncertain, we query the user, which in turn will provide a label to the machine learning algorithm. We also looked at machine teaching triggered by error. So, as you remember probably, machine teaching, the user is more proactive. So in this case, we have that the user has access to the output from the machine learning algorithm. And if they see that the estimation is incorrect, then this will prompt them to provide a label in turn. Of course, both these interactive learning strategies has to take the labeling budget into account. So they can only provide a label if it's enough labeling budget to do so currently. So we did the experiments on 2 different data sets. First, we have the mHealth dataset here, where 10 human subjects were performing a sequence of 12 physical exercises, and were recorded when they did so with wearable sensors on their body. Then we also have a synthetically generated dataset. And here we have randomly generated data instances divided up into 5 classes and having 2 features. So when we wanted to study the reliability of the user here, we did simulations to do so. And we looked at 2 different types or 2 different aspects of reliability that we focused on in this particular work. And these were reluctance and fallibility. And these were chosen because we thought they were most relevant for our particular problem setting. So reluctance then means that a user might not provide a label in accordance with whatever interactive learning strategy you're applying. And fallibility means that the user might sometimes provide an incorrect label. And in our experiments, we varied reluctance between 0 to 50% and fallibility from 0 to 50%. And in both these cases, the other factor or aspect was kept at 0. So onto the results. And this generated quite a lot of results, so I will only show a small number of this here. Of course, you can look into the paper if you want to see all of it. So if we start with reluctance, we found very unsurprisingly that increased reluctance led to decreased performance. And you can especially see that it sort of gradually gets worse as we increase reluctance. And as I said, this is very unsurprising because what it actually means in reality is that the machine learning algorithm has less data to go on, which means that it will get worse, typically, at least. But we also found in some cases that the gap in performance closed over time, as you can see in these 2 examples. And again, if you think about it, not that surprising possibly, because as time moves on, even the experiments where we had a high reluctance will sort of catch up with the 0 reluctance experiment. So in the experiments on fallibility, we found that the results varied significantly depending on the choice of machine learning method and interactive learning strategy. With regards to interactive learning strategy, the machine teaching typically had better results than active learning, but we found especially that the choice of machine learning had a bigger impact on the performance. So naive Bayes handles fallibility quite well, actually, as you can see in these 2 examples here. Even though we increased fallibility, so some labels are incorrect, it still performed quite well, or very well in some cases. But if we look at KNN and especially support vector machine, we have a significant drop in performance here. So here's an example from KNN. You still can see this decrease in performance. And if we look at support vector machine especially, and especially at the right figure here, we can see a very big drop as soon as we introduce any type of fallibility or any amount of fallibility into the experiment. So finally, some future work. So this work here we see as sort of an initial starting point, but of course you can expand on many different aspects of this work. For instance, you could look at more different types of machine learning algorithms and the other types of interactive learning strategies as well. You could also run the experiments on more data sets, and I think especially interesting to run them in real time with actual human subjects, because of course this was simulations, which has certain benefits. You can more decide which exact level you want, but of course if it's going to be used with actual human subjects, it's important to look at that as well. And of course also to further explore the reliability concept. As I mentioned, we chose to focus on 2 different types here, but of course you can look at other types and you can also expand on these 2 types in particular. So that was all from me. Thank you all for listening.
So thanks, Agnes, for your very interesting talk. So let's have a short round of questions. So So following your talk, I had a question about the way you are modeling the two different. How you're modeling the case where a user is not providing an answer versus the user is providing a wrong answer. So if I understood correctly, you would start with a data set that has full, complete, and correct annotations, and then simulate variability by flipping some of the, or I guess some of the labels, and reluctance by withholding some of the labels. Correct?
Yes, exactly. Yeah.
Okay. And did you look into, so as I understood, you would do this uniformly in the whole data set, right?
Yes. What do you mean with uniformly? But
yeah. Or let's say, so you would randomly decide which instances, so which labels would be withheld or which labels would be flipped. Okay. So what I was thinking is, there's a very interesting analysis that you did. It would be very interested also if that, let's say, for example, for the differences in the classifiers, if that remains also when you have changes in the biased flipping of the labels. So you could imagine that you are, for example, only flipping the labels of some class or of some particular feature. And it would be interesting to see how robust the classifiers would be against this kind of unequal variability, for example. Mm-hmm. Have you looked into this?
Well, I haven't done any concrete experiments on it yet, but it's definitely something we have thought about, and we're actually currently discussing this work with my supervisors, as I'm a PhD student, that we want to look a bit more further into this. And in these experiments, yes, we did this uniform, if you want to call it that, when we decided which data instances should be affected by the reluctance or fallible user. But definitely in certain scenarios, it would be more reasonable to assume that maybe certain labels would be, for instance, more difficult for the user to know the correct answer for, and so they should, in that case, possibly have a higher probability of being incorrect, let's say. So it's definitely something, yeah, I agree with you. I think it's definitely something that could be interesting to look further into. So I don't really have any, I haven't done it yet, but it's definitely something we will look into, if I put it like that.
Mm-hmm. Yeah, thank you. That sounds interesting. Yeah, there are other questions concerning the Agnes presentation.
Can we see them here, or yeah, it's a Q&A down here. Yeah.
Yeah, the Q&A is down there, but
it's clean now.
And there's sometimes a show of hand, but at the moment not. So yes, but I think we probably, yeah. In that case, let's move. I think let's thank Agnes again, and then I will hand over my chair role to Daniel to chair the last session of our workshop and to announce the invited talk.